MPLS stands for Multiple Protocol Level Switching. So MPLS at the beginning, it is produced to speed up the data forwarding because we know our traditional IP forwarding, we must need to search the IP routing table. And when we search the IP routing table, we must use the longest must match to search the IP routing table. So it takes a long time to forward the IP packet. So we produce the MPLS to help us to speed up the data forwarding on the devices. So this lecture, we are going to learn the two planes of MPLS. One plane is control plane. The other plane is forwarding plane, or we can call it data plane. Okay. So control plane, you can think if it is in IP network, the control plane is a process that we build the IP routing table. So control plane is a process to build the table. In IP network, it's a process to build the IP routing table. In MPLS network, it will be the process to build the MPLS level switching table. That is control plane. After we have built the table, we need to forward the data, right? Okay, so we will go to forwarding plane. In the forwarding plane, if it is IP network, it will be the IP packet be forwarded by the IP routing table. We search the IP routing table and forward the data. And if it is in MPLS network, it will be like we will search the MPLS level switching table and then we forward the MPLS packet. So you just remember all of this lecture, we will follow these two plans, control plan and forwarding plan. Okay? So upon completion of this course, you will be able to describe the background and typical applications of MPLS, describe the basic concepts and working principles of MPLS, describe the process of MPLS data forwarding. First, let's look at the MPLS overview. This is a traditional IP forwarding, and on router A, B, C, D, we have a packet on router A, received on router A, and the destination is 10.2.0.1. So how do we forward this data? We will search the IP routing table, and we will use the longest must match principle to search the IP routing table to find the destination and to find the next hop. Then we will forward it to the next hop. So router A will give it to router B. So on router B, we will do the same process, the same action, search the IP routing table, find the next hop, and then give it to next hop. On router C, also give it to next hop. Finally, on router D, we search the IP routing table, find the next hop, and give to the destination network. So this is the traditional IP forwarding. Because at the beginning, the performance of the physical equipment is limited, and the IP routing table is very large. And if the IP routing table is too large, it will reduce the processing time of the physical equipment. That's why we need to think about a way to speed up the forwarding speed. Then we produce the ATM technology. ATM technology means asynchronous transfer mode. On the ATM table, we don't need to care about all the destination networks because packets, they may want to go to different destination. So we don't need to maintain this table. We just need to maintain the table with a label. That's the label only help us to go to the next hop. So this reduces the size of the table because the table is small and the forwarding is very simple. So In this way, it can help us to speed up the forwarding speed of the data. So MPLS is like the IP forwarding and ATM together. We produce the MPLS. So MPLS, we use label to forward the data. And if we have a data, and this data have an IP header, and then we will add a new header, MPLS header, to the traditional IP packet. So in the MPLS domain, we don't need to check the IP header. We don't need to check the IP header, check the destination IP to check the routing table forward the data. We only need to check to process the MPLS header. In the MPLS header, we will have the labels. So we will search the MPLS label table to search the table to find the next hop, then to forward the data to the destination. So this is MPLS label forwarding. Let's look at it. When router A receives an IP packet, because router A is the ingress of the MPLS domain, so the router A, it will push a label, MPLS label. This label is MPLS is contained in the MPLS header. So this label is 1024 and send it to router B. When router B receives it, it will search the MPLS label switching table. And because the incoming label is 1024, so he searched the table, he will find the outgoing label is 1029. So he will swap this label to this label and then forward it to the next hop, router C. When router C receives this packet, he will process in the same way. The incoming label is 1029. He will swap the label to 1039 and send it to next hop router D. And when router D receives this, he search the label switching table. He find the incoming label is 1039. The corresponding action is pop. So he will remove this label and send it to the destination. When router D send it to the destination, it will use the IP forwarding again because router D is the egress of this MPLS domain. It means router D is the last hop of the MPLS domain. Okay, so this is MPLS label forwarding. And nowadays, because the performance of our equipment, the performance of the router, performance of the switches is very, very good. So we don't need the MPLS to help us to speed up the data forwarding because it's the same. Even if we use IP forwarding, the speed is the same with the MPLS forwarding. So MPLS now it will be used in some VPN application. For example, MPLS VPN. So in this MPLS domain, it's always be the ISP. So in the ISP, we have different customers. So these customers, they have the requirement to communicate with their remote site. For example, customer A, this is the headquarter of customer A, and this is a branch of customer A. So they have the requirement to communicate with each other through the ISP, through the internet. So they will purchase the MPLS VPN from the ISP. So that is the application of MPLS. And we can use MPLS VPN to distinguish different enterprise and different VPNs. Another application is MPLS TE. TE means traffic engine. So with MPLS TE technology, for example, we can control the traffic to use the different paths, to use a different link. For example, for network A, if we want to go to the destination network C, we have two routes, we have two ways. One way is to go to A, go to B, C, D, and E. The other way is to go to A, B, G, H, D, and E. So we can use the TE to control the traffic. 70% of the traffic we will use this way because we can see this link is larger. The bandwidth of this link is larger than this link. So this link will be the primary link, and the 30% of the traffic will go this way. This way, the bandwidth of this way is lower than this way. And also for network B, the same. We can use traffic engine to control 70% of the traffic to use the primary link and 30% of the traffic to use the secondary link. Okay, now let's go to the next chapter, MPLS basic principle, MPLS control plan and forwarding plan. So this is the MPLS network model. In this model, we can see here, this is the MPLS domain. MPLS domain means the routers that running MPLS protocol. So in this domain, we have several rows of MPLS router. First row is LER. LER means level edge router. Level edge router. So in this network, we have two LER, router A and router D. They are two LERs because router A and router D, they are at the edge of this MPLS domain. Okay, and the other row is LSR, level switch router. So all the other routers, router F, router G, B, C, and E, all the other routers in the middle, they will be LSR. And another concept is LSP, level switch path, LSP. LSP also, we can call it tunnel. Okay? Because when we give our IP packet to the MPLS domain, to the LER, the LER, it will push a label to this packet. And when this packet is forwarded in the MPLS domain, it will always with the label. So the packet is label switched in the MPLS domain. And this path from the source to the destination, from router A to router D, this path, we call it LSP. From the source to the destination, we call it LSP, and we can also call it a tunnel. And the MPLS control plan and forwarding plan, this is a model, the architecture. So for the control plan, first, routing protocol. What's the function of routing protocol? So the routing protocol can help us to calculate the routes, to learn the routes, to build the IP routing table, And at the IP routing table, can help us to build the IP forwarding table. The IP routing table and IP forwarding table, you can regard them as the same thing. Once IP routing table is in the control plan, IP forwarding table is in the data plan. Actually, they are the same thing. When we need to forward the data, we need to use the IP forwarding table. But the IP forwarding table, it is the same with the IP routing table. Okay, and then we need the label distribution protocol. Label distribution protocol. Why do we need this? Because we want to build the label forwarding table. The label forwarding table. Why do we need the label forwarding table? Because in the MPLS domain, we don't need to use the IP routing table because we don't process the IP header. We just need to process the MPLS header. And in the MPLS header, we have label. We have the label. So we just need to check the label and to search the label forwarding table to find the outgoing label and the next hop, the outgoing interface and the next hop. Then we can forward the MPLS packet to the next hop. Okay, and continue. Let's look at when we receive an incoming packet, what will happen? First, if we receive an incoming IP packet, for example, this is an LER. LER is Label Switching Edge router. So the edge router, it will receive the IP packet. When we receive an IP packet, we will search the IP forwarding table. We will search the IP forwarding table. When we search the IP forwarding table, there will be two situations. One situation is this IP packet doesn't need to go to the MPLS terminal. So we will search the routing table and outgoing IP packets. So it will be the traditional IP forwarding because this packet doesn't need to go to the MPLS terminal. The other situation is this packet needs to go into the terminal. For example, this packet, the destination is the terminal's end, is the end IP address, is the destination IP address of this terminal. So we have to give it to the MPLS terminal. So we will outgoing the labeled packet. It means we will push an MPLS header to this IP packet and then forward it to the next hop, Okay, so when this packet goes to the next hop, for example, the next hop, LSR receive an incoming labeled packet, So this packet is with the MPLS header. And then it will search the label forwarding table. When it searches the label forwarding table, we will find that what is this incoming label? What's the incoming label? And we will find the incoming label's entry. And this entry, it will also have two situations. One situation is if this LSR is in the middle, it's not in the edge, it's in the middle. So we will find the outgoing label and swap the incoming label to the outgoing label and then forward this packet to the next hop. So this is in the middle, the LSR. If we are not LSR, we are LER. We are the end of the MPLS terminal. And when we find the incoming label, we find there's no outgoing label. And we need to pop the MPLS header. It means we are the last hop of the MPLS terminal. So we will pop the MPLS header and then continue to process the IP header and forward this IP packet based on the IP routing table. Okay, so that is the control plan and forwarding plan of MPLS. Continue, let's look at the MPLS label format. For the MPLS label format, we have two kinds of modes. One is frame mode, the other is cell mode. And cell mode is only used in ATM. So we will not discuss this mode in this lecture. So this lecture, we will learn the frame mode. For the frame mode, let's look at this. This is a traditional layer 2 frame format. The payload, then the IP header, then the layer 2 header, the frame header. Sometimes it's PPP, sometimes it's Ethernet. Okay, so for the MPLS frame, we will insert a MPLS header between the layer 2 header and the IP header, the layer 3 header. We will insert an MPLS header. So this is the format of MPLS header. The length of MPLS header is 32 bits. 32 bits, and the most important part is label. So because we will use this label to forward the MPLS packet. And the next field is EXP. EXP is used for QoS. And S means bottom of the stack. Bottom of the stack, because MPLS header, it supports the nesting. The nesting means we can have multiple MPLS header. We can have multiple labels. So how can we know this header is the bottom of the stack? So we can check the S. If the S is 1, it means this is the bottom stack, bottom of the stack. This is the last MPLS header. If it's not 1, if it's 0, it means we still have other MPLS headers after this header. Last field is TTL. TTL is used to prevent the loop. So it's similar to the IP header, TTL. MPLS label nesting. So we know that we can have multiple MPLS headers. It supports the nesting. So for example, we have level 1, level 2, and level 3. So on the in the level 1, the S bit will be 0 because it is not the bottom of the stack. On level 2 also S will be 0. In the level 3, the S will be 1 because level 3 is the bottom of the stack. Okay, and the applications of label nesting is MPLS VPN and MPLS TE. In MPLS VPN, we have two labels in MPLS VPN. One is outer label. The other is inner label. We can also call it public label and private label. Okay, next, MPLS forwarding process. Now we need to learn two concepts. One is FEC, the other is NHLFE. FEC stands for Forwarding Equivalence Class. FEC is a set of data flows with certain common characteristics. These data flows are processed by the LSR in the same way during the forwarding process. In the same way during the forwarding process. What does it mean? It means, for example, you have 100 packets, and these 100 packets, they have the same destination address. They have the same destination address for this 100 packets. So this 100 packets will be the same FEC, since they will belong to the same FEC. It means in the MPLS network, when we need to forward this 100 packets, we will use the same way. So that is FEC. The other concept is NHLFE, stands for Next Hop Level Forwarding Entry. Next Hop Level Forwarding Entry. So the NHLFE is used for level forwarding. It will guide us to forward the MPLS packet. It will tell us What is the next hop of the packet? How to perform a tag operation? A tag operation, we have three operations. One is push. This is always been done on the ingress. On the ingress, we don't have any label, so we will push a label to the packet. And pop. Pop is always been done on the egress. On the egress, the last hop of the MPLS terminal, we will pop the tag and use the traditional IP forwarding. The last is swap. Swap is used in the middle in the LSR. Swap means we just swap the one level to another level and then forward it to the next hop. So the NHLFE will guide us to forward the MPLS packet during the MPLS terminal. So this is an example of FEC and NHLFE. We can use display MPLS LSP include 10.2.0024. So 10.2.00/24, this is an FEC. This is an FEC. So all the packets want to go to this destination will belong to this FEC, 10.2.00. And for this FEC, what kind of NHLFE should we follow? So let's continue. The NHLFE, it will be the next hop is 10.1.1.2. And in label is none because this is the ingress. So the in label is none. Out label is 1030. So we will push this label to the packet. Out interface 0, 0. And the label operation is push. So this is one NHLFE used for this FEC 10.2.00. Okay, so let's continue to look at the MPLS forwarding in the ingress LER. On router A, ingress LER, when we receive a packet 10.2.0.1, so this is an FEC. This is an FEC. So we will check the table to find the FEC is 10.2.0.0. When we find this FEC, we will continue to check the NHLFE of this FEC. So the NHLFE is the out interface is 0, 0. And the label operation is push. It means we will push a label to this packet. And the out label is 1030. So we will push the 1030 label and send it out from 00 to the next hop device, router B. Then continue. The router B is the transit node. It's in the middle. So on the router B, we will search the ILM, stands for incoming label map. Incoming label map table. In this table, we just search the in label, because router A sent a packet to router B and the in label is 1030. So we will find the NHLFE of this in label. We will find the out interface is 0, 3 and the label operation is swap. And the out label is 1032. So we will swap 1030 to 1032 and send it to router 3. When router C forward the packet continue to router D, and on router D, we will still the same. We will search the label switching table, And in the label switching table, we will search the in label, and we will find the in label is 1032. And for this in label, we will find the corresponding NHLFE. The NHLFE is label operation is POP, and there's no out interface. So on router D, we will pop this label and continue to use the traditional IP forwarding to forward this packet to the destination network. Okay, that is all. So now let's look at two questions. First, which field in the MPLS header is used to identify the stack bottom level? Because the MPLS header, it supports nesting, so we can use CS field to indicate whether this header is the bottom of the stack or not. Question number 2. Which of the following actions can be performed when packets are forwarded based on MPLS levels? There are 3 actions. First is push. This is always used on the ingress LER. Second is swap. Swap is used in the LSR in the transit node. The last is pop. Pop is used as the last hop. Is in the egress LER. We will remove the MPLS header and then use the traditional IP forwarding. So finally, A, B, 3 options. So let's look at the summary of this lecture. First, we learn the background of MPLS VPN. The background of MPLS. Why do we need MPLS? Because at the beginning, we want to speed up the forwarding speed of the data. Second, we learn the basic concepts of MPLS. We have LER, LSR, and LSP. MPLS packet formats and MPLS forwarding principle. And we will use the label switching table to search the label switching table to forward the MPLS packet. As a key technology of SDN, SR stands for segment routing, is also a key technology for simplified protocols advocated by IP networks. It is widely used in IP networks. So this course will analyze the SR technology. Upon completion of this course, you will be able to describe the advantages of SR, describe the basic concepts and working principles of SR. First, let's look at the first chapter, SR technical background. The first background is problems faced by LDP. We know that for MPLS, we have several protocols that can help us to distribute the labels, and LDP is one of them. And one problem of LDP is LDP depends on IGP and uses local label switching to support equal cost multiple paths. So it means if we want to run LDP, first we must run IGP protocol such as OSPF or ISS. They must have learned the IP routing information. Then they can use LDP to distribute the labels. And the disadvantages of LDP is LDP has 11 types of protocol packets, which greatly increase the link bandwidth consumption and device CPU usage. So LDP is too complicated. And another problem faced by LDP is LDP supports only the shortest IGP path for path calculation. It means, for example, on this router, if we want to go to this destination, because we will choose the shortest path by the IGP, learned by the IGP. So the IGP will calculate This cost is 10, this cost is 10, but these two costs are 20 and 20. So after the calculation, IGP will think this path is the shortest path. So the LDP, it will also distribute the labels during this path. So it will not use this path at all. So in this way, we will waste the resources of this path. That is the disadvantage by LDP. And traffic engineering is not supported by LDP. We cannot control the traffic to go both of these two links. The other link, the other label distribution protocol is RSVP. RSVP, this protocol creates an end-to-end LSP hop by hop based on the CSPF path calculation result. The label is a local label. So the hop by hop traversing nodes maintain the status of the tunnel. Even if SDN is used, the tunnel status needs to be maintained. And RSVP TE configuration is complex. Complex, easy cost implementation. If we want to implement the equal cost multiple paths, it is very complex. And there are 8 types of RSVP protocol packets, so it will occupy network bandwidth and CPU processing. Another problem of RSVP is complex in load balancing, and for example, in this topology, if we want to load balance among these two links, among these two paths, it needs to be configured with multiple tunnels, and which brings huge workload to configuration and maintenance. All of this, the load balance, all of these tunnels needs to be configured manually by the administrator, so it's a lot of work. Okay, after talking about the LDP and RSVP, let's look at the SR generation background, the SR technology. Here we have 3 kinds of network. First is the traditional network. In the traditional network, we can see these are the network devices. Because our network, we can have 2 planes. One is control plane. The other is forwarding plane. Okay. In the last lecture, we have learned what is control plane, what is forwarding plane. Control plane is a process that helps us to build the tables. Maybe it's MAC table, maybe it's routing table or MPLS table. But if we want to build the tables, that is control plane. So control plane stores the forwarding information for us, for the devices. And forwarding plane is to follow those tables that has been built in the control plane to forward the data. So that is forwarding plane. And for the traditional network, both control plane and forwarding plane, they are integrated on the network devices. So it requires a very high performance of the network devices. Because all of these planes, both of these 2 planes, they are working on the network device itself. Okay, so this network is SDN network, the revolutionary SDN network. Network faults in the SDN network, the network faults can be rectified only when the controller is faulty. The reliability is very poor. Okay, for the SDN network, we use the controller. It's a new device. We use the controller to separate the forwarding plane and the control plane. So it means the control plane does not need to work on the network device. All the control plane is working on the controller. And the network device will only use we only need to use the network device to forward the data. And all the tables, including the routing table, MPLS table, any tables, they are calculated and they are working on the controller. So it requires a very high performance for the controller. But for the network device, we don't need too many resources on the network device. So the SDN network, it release the performance of the network device to make the network device emphasis on the data forwarding, not on the control plan, not on the calculation of the route. Okay, but this this kind of network, it is a subversion of traditional networks and is not supported by equipment vendors and carriers. So we create this incremental SDN network, which is today's topic, segment routing (SR). For this kind of network, the existing protocols can be expanded to achieve better smooth evolution. So we don't need to separate all the control plan and forwarding plans on the controller and on the network device. So the controller, it can have part of the control plans, and also the other parts of the control plans are still on the network device. So it can provide the balance between centralized control and distributed deployment. It uses the source routing technology to provide fast interaction between the network and upper layer applications. So that is segment routing. Okay. And the segment routing technical framework is like this. Like before, it also has control plan and data plan. Another thing, for the path selection, we have two ways. One way is path computation. This is use SPT computation. For example, we use SPF algorithm to calculate the path. This is one way. The other way is we can use the explicit path. This can be a segment list. In this list, for example, on the source node, it will have all the information about the forwarding path, and it is better used for path control. On the source node, we will know all the paths to the destination. We will know the whole path to the destination on the source. So it will be easy for us to control this path. And we expand the traditional protocol like BGP, like SS. We expand those traditional protocols and communication to make it communicate with the controller so they can help us to collect the topology, program path, and device information. So that is the SR technical framework. To look at the second chapter, SR principle analysis. First, basic concepts of SR. For SR, let's look at some basic concepts. First is SR domain. SR domain is easy to understand that it indicates the set of SR nodes. So if we are running SR on those devices, so all of these devices will be in the SR domain. Next is segment. For the segment, you can think the segment is first is the self. It's the node itself. First is the node. The node means one router. So one router is a node. Second, prefix. Prefix means if you want to go to some destination, so that destination is a prefix. Next is adjacent. The adjacent, you can regard adjacent as the path, as the link. Okay, so these three, one is node, and one is prefix. The prefix can be one destination IP address. And adjacent. Adjacent, you can regard the adjacent as a link. This link is adjacent, but adjacent, it has direction. For example, this direction is an adjacent, and this direction is another adjacent. So that is segment. Next is segment ID. Okay, now we have known the segment. Then we need to give each segment, each node, each prefix, each adjacent an ID. So this ID will be unique in the SR domain. We will use the SID, segment ID, to forward the data. So it's very important. Next is sRGB, segment routing global block. You can think this is the resources of the ID, of the SID, the resources of the ID. We have a pool of the segment ID, and this pool is the sRGB. Okay, next is the segment list. Segment list, it is a short set of destination address, prefix SID or node SID and adjacent SID ordered list. If you want to go to some destination, for example, you are on the source router, you want to go to this destination, you need to have a list. And this list maybe include the node SID or prefix SID or adjacent SID. So this SID will help you, will guide you to forward the data to the destination. Okay, so these are the basic concepts of SR. Okay, so let's look at the detailed. We have know what is segment, okay? And segment, there are three types of segment. One is adjacency segment. The other one, prefix segment. Last one, node segment. For the adjacency segment, this is one router. This router, it has three links, three interfaces. And these three interfaces and this direction, we will have three adjacency segments. We have three adjacency segments, okay? And second is prefix segments. For the prefix segment is one network. One network. If we have a network address is this. So we can give this network prefix an SID. So this SID will be prefix SID. For example, we give this SID 100. The last one is node segment. The node segment, for example, in this network, we have three nodes, three routers. So each router, we configure a loopback address. And this loopback address, we will give the loopback address one node ID. The node ID is 101 or 102 or 103. Okay, so node ID is the third segment ID. Okay. Okay, so in this network, the destination prefix is this, and we give the prefix ID is 100. Okay? And from the source to the destination, we can use the path of this or use this path. And on PE1, if we want to go to this destination, we need to go to P1 first, and P1's node ID is 2001. So here is 2001 and then go to P1. And P1, if he want to go to this destination, he needs to go to P3. And for P3, the node ID is 3100 for the same. And P3 want to go to P5, then P5 want to go to PE2. Finally, go to this destination network. This is prefix segment. And adjacency segment. For the adjacency segment, this is it's a link and direction. The link and direction. For example, this link and this direction, the adjacency ID, adjacency segment ID will be 102. This link and this direction, it will be 205, and this 405, 507, 709. Okay. And on the source on PE1, if we want to go to PE2, and we use the segment list to help us forward the data to PE2. So this segment list on PE1, it will indicate the whole path, to the destination. For example, first on the top is 102. Okay, so 102 is from P1 to P1 is 102. So we will remove the 102 and give it to P1. And P1 on the top, it will be 204. For 204, it's P1 to P3 is 204. So we remove 204 and send it to P3. So it's the same. From P3, remove the top segment ID, give it to P4, and P4 to P6. Finally, P6, find for 709 is to go to PE2. So he will remove 709 and give it to PE2. Then PE2 will get the original packet. So he will search the IP routing table to forward the original IP packet. And next, it will be adjacency segment plus node segment. Adjacency segment plus node segment, it is a combination of an explicit path and a shortest path. It's called a loose explicit. It is mainly used for SRTE, for the SR traffic engineering. Okay, so for example, on PE1, we want to go to this destination. So we check the segment list. On the top is 1101. Okay. Now you need to remember, if the top is not the adjacency segment ID, if this is a node segment ID, for example 1101, so who is 1101? And PE1 is 1101. Okay, so PE1 will receive this, and PE1 check the table. It will find now that on the top, the label will be 2101. And who is 2101? Is P1. So he will find the shortest path to P1 and send it to P1. When P1 receives it, continue, he will change 2101 to 3101. And who is 3101? It is P3. So he will change. So he will check the shortest path to P3 and send it to P3. On P3 it's the same, 3100. So he check who is 3100. It is P4, and on the list, the next segment list, the segment ID is 405, and 405 is this adjacent segment ID. So he needs to remove the 405 and 3101, then give it to P4. When P4 receive it, he will swap 3100 to 2100, which is P6, and continue send to P6. And P6 the same, swap it to 1100 and send it to the PE2. Finally, PE2 remove 1100 and forward it to this destination. So this is adjacency segment plus node segment. And sRGB, that is label resources. For the label resources, different device, they can have different label resources, or we can configure the same label resources for different devices. Okay, let's continue the next chapter, SR working principle. For SR working principle, so First, let's look at this. SR is a protocol designed for forwarding data packets to the network based on MPLS protocol and based on the source routing technology. Okay, so first on this router, we want to forward this data. And for this data, it has a segment list. In this segment list, we have maybe it's the node segment ID, maybe it is the adjacency segment ID. Okay, so let's look at it. On the top, remember, on the top, if it is the adjacency segment list, it will be easy. We just find the right adjacency and forward it to the next hop. But if it's not the adjacency segment list, segment ID, if it is a node segment ID, for example, 101. So who is 101? This router, node ID, node SID is 101. So now this router, we will need to use IGP to find the optimal path to 101. Okay, so for this router, how can we reach 101? By IGP. By IGP, if the cost of these two paths are the same, so we will use the ECMP load balance to send the traffic to node SID 101. And when this router receive the data, receive this packet, it will remove 101. When it remove 101, now on the top ID is 1006. So it will search the table. 1006 is the adjacency ID, SID. So it will send it to this device. The next hop will go to this device and remove the 1006. When this router receive it, on the top is 2006, and the 2006 is this adjacency ID. So send to this router. Finally, this router, the segment list is 100, and segment list is 100. He will search the table and find the destination is this router. So he will forward the data to this router. So that is the forwarding process of segment routing. And now let's look at the control plan of SR. For the control plan, we need to use ISIS, the expand ISIS protocol. So how does it work? For the forwarding plan, just now we can know that if one source wants to go to some destination, we must have a list, the segment list, right? And we must have the table. So how can we learn this list? How can we get this list? How can we learn those node ID or adjacency ID? So we can use ISIS. For example, on PE2, we configure loopback address, and the node ID is 10. And now we are running ISIS protocol. So ISIS protocol will help us to flood this node ID to all the other neighbors. And other neighbors, when they receive it, they will continue to flood this node ID to other neighbors. So the whole network devices, they will learn the node ID of PE2. Okay? And now here we can see on PE1, if we want to go to this node 10, we have two paths. Based on the ISIS calculation, we have two paths. These two paths, they have the same cost, okay? And for PE1, for this path from PE1 to P1 to P2 and to PE2, for this path, first, the out label is 210. 210. So 210 will be the adjacency SID of this link. And then from PE1, from P1 to P3. Out level is 410. So 410 will be the adjacency SID of this link. And the same here will be 610. Here is 610. Finally go to PE2. And the other path is similar, but it should be different. The SID should be different. Out level, they are different. Okay. And then if from PE1, he wants to go to the destination PE2, he will use these two paths to forward the data to this destination. And these two paths are load balanced. And for the data plan, so let's look at the data plan. On PE1, if we want to go to PE2, when we receive some packets and we want to give it to PE2, so first we will push the label to the packet. Because it's load balanced, so one packet we will push 210, which is the out label of this path. So we push 210 and send it to P1. When for P2, we will push 310 and send it to P2. Okay. For example, for P1, when P1 receive it, he will check the label is 210. Okay, the in label is 210. So I will swap 210 to 410 and send it to P3. So P1 will swap 210 to 410 and send it to P3. Let's continue. Yes, so P1 swap 210 to 410 and send to P3. And when P3 receive this, P3 will check this table and the in label is 413. So P3, it will swap 410 to 610 and send this packet to P2. And when P2 receives this packet, he will check the in label is 610 and out label is none. It means for PE2, there is no out label. So PE2 is the last hop of this tunnel. So PE2, it needs to pop this label. So PE2 will pop this label and forward this packet based on the traditional IP forwarding. Okay, and so this is next the control plan of the SR. So in this topology, we can see P from all of these devices, they have the node ID. So each device they have a node ID, and all the links, two directions, they have the adjacency SID. So there is one question. How do they learn the SID and the node SID and the adjacency SID? So they will use the ISIS. Protocol. So ISIS protocol will help to flood all of the SID to the neighbors. Okay? And then BGP, link state protocol, is also an expanded BGP protocol. BGP-LS protocol, it will collect all of this topology information, all of this SID to the controller, okay? And then the controller, it will use PCEP protocol to calculate the path from the source to the destination. It will use this protocol to calculate the path from the source to the destination. And finally, the controller, it will use netconfig this protocol to give this path to the source routing, to the source router, because PE1 is a source router if he wants to go to PE2. So the controller knows the whole topology and the whole SID. So the controller will give this list to PE1. So PE1 will get the list. If he wants to go to PE2, first he needs to go to 501, and 501 is this, and then 103, 103, and then 304, and then 406. Finally, go to PE2. So that is how does SR work. So on PE1, we will have a tunnel between PE1 and PE2. So how does PE1 forward the data through this tunnel? We can just check this segment list, and we will find on the top is 501. So for 501, we will just give it to 501's adjacency, 501 adjacency, and give it to P1. And when P1 receive it, it will be 103 on the top. So we will give it to 103, this adjacency, and give it to P3. And when P3 receive it on the top, it will be 304. So 304, we give it to P4. And when P4 receive it, on the top is 406. So 406 is this way. So we give this packet to PE2. Finally, when PE2 receive it, it is the original packet, and the PE2 now it will use the traditional IP forwarding to forward this packet to the destination. And another way, now we just learn, what we just learned, we call it strict explicit path. What does it mean? Strict explicit path means on the source device of this path, we have known the specific path to the destination, all the links, all the hops, hop by hop, we have known the whole specific path to the destination. That is strict explicit path. Another mode is loose explicit path. For the loose explicit path, for example, on router 1, the top is 1004. And 1004, it is not an adjacency SID, but it is a node SID, which is P4. It's a node SID, which is P4. So PE1 first needs to go to the node P4. So how does PE1 go to the P4? We will use the IGP to calculate, to find the shortest path to go to the P4. And this shortest path, we don't know, we don't have the SID. And this is all by the IGP to find the shortest path to P4. So P1 send it to P2, P2 the same, find the shortest path to this node, to P4. When the packet reach P4, P4 will find on the top, this node ID is itself, so it will remove the 1004. When it removes the 1004, it will be 403 on the top. And 403 is not node ID, but 403, it is an adjacency SID. So we can forward this packet to this, through this link to P3 and remove the 403. When P3 receive it, 306 is on the top. So P3 will forward it to 306 and remove this label and give it to PE2. Finally, PE2 will receive it. So this is another mode, loose explicit path. Okay, that's all. Now let's look at two questions. First, which of the followings are the SR tunnel type? The answer is A, SRBE tunnel, best effort. B, SR traffic engineering loose explicit path tunnel, and D. SR traffic engineering SRTE strict explicit path. Question number 2. Which of the following actions may be performed when packets are forwarded based on the SR label? So it's similar to MPLS. We will have three actions. One is push, one is pop, and one is swap. So the answer is A, B, C.